you all? Darrell Lee Berry Jr. back for some more problem solving in thermodynamics, finishing from where we left off yesterday. As far as I can tell, everything is looking fine with the levels of everything. I'll check to be sure. And anybody who drops in, let me know if anything is not coming through clearly, but it seems to be fine on my end. Showing live. All right. So we'll go ahead and start the problems, continuing from what we had before. And we left off on this slightly complicated problem, 1.16, calculating the pressure of air given height in the atmosphere. So we'll see where we leave off from there, 1.17 C and D. Because even at low density, real gases don't quite obey the ideal gas law. A systematic way to account for deviations from ideal behavior is the virial expansion. Right. So we I think this is one that is definitely not on my formula sheet. So let me add this one. Seems correct. It's running a bit long, but got some stuff on the back for the time being. Maybe I'll make some more space in other ways. I didn't realize, by the way, that this is the monomial expansion. I guess I should say N. This is the expansion of that, at least the logarithm of that, right? Where the functions bt, b and c, and so on are called the virial coefficients. When the density of the gas is fairly low, so that the volume per mole is large, each term in a series is much smaller than the one before. In many situations, it's sufficient to omit the third and concentrate on the second, whose coefficient bt is called the second virial coefficient. First coefficient being 1. Here are some measured values of the second virial coefficient for nitrogen. So we can see how that changes with temperature. Think about the forces between molecules and explain why we might expect. So hold on, I'm doing only C and D. Then he proposed a relationship between PV and T, like the ideal gas law or the Vero theorem, is called an equation of state. Another famous equation of state, which is quantitatively accurate even for dense fluids, is the van der Waals equation. And I believe I do have the van der Waals. No. A n squared over v squared v minus nb equals n big R capital T. Right, that's correct. So P plus an squared v squared v minus nb equals nRT, where a and b are constants that depend on the type of gas. Calculate the second and third virial coefficients B and C for a gas obeying the van der Waals equation in terms of A and B. Hint, the monomial expansion says that 1 plus x p is similar to 1 plus px plus 1 half p minus 1 squared, provided that px is less than 1. It's much less than 1. Prior this approximation to the quantity, right? 1 plus x to the p power is similar to 1 plus px plus 1 half p minus 1 x squared, given that the absolute value of px is much less than 1. Right? Let's see what the solution said about this. Solving the van der Waals equation for P and factoring out NR over V on the right hand side puts it in this form. Check the problem again. Calculate the second and third virial coefficients. So seems like what we want to do is put the van der Waals equation van der Waals in this form. So I'll just copy it. I don't know what I did the first time I did this, but it seems to be easier than I expected. So I'm gonna get the viral expansion, which is this. I need to put the van der Waals equation in this form. So I need to just put PV on the same side. This is solve it for P. So P plus AN squared over V squared equals N big R big T over V minus NB. And we have P equals nRT over V minus NB, capital V, minus AN squared over big V squared. Factor out nRT over V. So this equals nRT over V. Uh, 1 minus NB over big V minus AN squared over N big RT V C. V is already there. I'm dividing by V, so at least one V. V. That equals N big RT over V. 1 over 1 minus NB over big V minus AN over N big R. Actually RTV. And this is what the book has. So since I'm solving for the V coefficients, all I have to do is put the van der Waals equation in this form. So we want to solve for the coefficients of the virial expansion. All we have to do is put PV by itself, just like PV equals nRT, and then we're left with those coefficients. The second term on the right-hand side is already in the form of temperature-dependent coefficient over Vn. It means nRT over V, 1 minus 1 minus NB over V minus A over RT Vn. So we're putting it into the Vn form because I noticed that Vn is in the denominator. So we have Vn in the denominator. Now notice that there's a 1, so it seems like I need to factor this denominator out as well, but then I would have to multiply something into the second part to see what they say. So since that is Vn, attributes to Bt. Whatever has Vn in it contributes to Bt. So if it has it as a multiple. To get the first one in proper form, that's when we have to utilize the expansion they gave us. I believe I put that on my formula sheet, which would be this. See if it works. So we're going to expand 1 plus negative NB over V to the 1. So that's going to equal 1 plus 1 times X, which is negative NB over V plus 1 half 1 minus 1 X squared be this. Expansion should be valid at low density when Vn is sufficiently N over V is thus the van der Waals equation takes the approximate form. You'll get the same exact thing. Because everything else is 0 when I do it this way. Apparently I need to get more familiar with the binomial expansion. Saying that this equals one plus NB over V plus NB over V squared. That's 1 plus negative NB over V and negative 1, an exponent. One minus 1 plus minus NB over V to the negative 1. That's 1 plus NB over V plus NB over V squared. This is correct. So one thing I have to remember is a lot of these things are simpler than they seem. Right? So that means it equals nRT over V, 1 plus NB over V plus NB over V squared minus A over RT over V. From this expression, we can read off the second and third variable coefficients. And BT is B minus A over RT. Okay. Because, and this is, I wrote this incorrectly. So basically, I can rewrite this as nRT over V1 plus NB minus A over RT over Vn plus NB Vn squared. So B T equals NB minus A over RT, and C T equals B squared, they said. So the N is apparently not included in the coefficient. So using 1 mole. Because A and B are positive, BT is positive in high temperature limit and negative in low temperature limit as desired. All right, so everything looks good with my screen. So let's go to D. D says, plot a graph of the van der Waals prediction for BT choosing A and B so as to approximately match the data given above for nitrogen. Discuss the accuracy of the van der Waals equation over this range of conditions. So I shall skip this graph part and we'll go to the next problem. So the next problem is 1.20. Key takeaway here, by the way, is if you want to get the coefficients of the virial expansion, just put it in the virial expansion form. PV equals nRT, just solve for PV. Sometimes you might have to take a roundabout step. Like first I had to just put V on one side and then solve for V over there. Solve for something over V, so then I can multiply V over. So sometimes there's a roundabout way to do it. One then the other, so I have to keep that in mind. Solve for P, solve for 1 over V on the other side, and you can multiply V over and still have nRT on the outside. If anybody wants to ask questions, remember that I'm on Discord. You can see the Discord streaming at the top. Be sure to like and subscribe if you haven't already, and we'll keep it going. And if you make a chat, I'll be checking chats as well. See if anybody has any questions about anything. All right, so 120. Right? 120 says uranium has two common isotopes with atomic masses of 238 and 235. So U 238 and U 235. I wonder why they mention Alora's number for second. One way to separate these isotopes is to combine the uranium with fluorine to make uranium hexafluoride gas, or UF6. Then exploit the difference in the average thermal speeds of molecules containing the different isotopes. Calculate the RMS speed of each type of molecule at room temperature and compare them. I believe that's the whole problem. So let me make sure I have RMS on my sheet. I believe I added that, but did not. I will add it now. The RMS is right here. Let's see if I have it correct. I'm missing a 3. Right, that'll be a big problem. I do remember this 3. I must have added it on my class page, but not this page. And that's for the 3 degrees of freedom of the motion. So VRMS equals square root of 3 RT. Crap. Would be a R. Several things wrong with this equation. VRMS equals square root of 3 RT over M. And notice they have a capital M here. Not sure if that makes a big difference, but I'll go ahead and make it capital M just in case. All right, this should be correct. VRMS equals square root of 3 RT over M. So R equals 8.31 joules over K. Room temperature, T room equals 300 K. And the mass right? So a UF6 molecule containing uranium 238. So let's check the molecular mass. We're on page 19. All right. So fluoride is 19. Right. So F6 equals put it back in my set, right? So we have 19 times 6 equals 114. And U238 equals, let's find this. Suppose it means the 238. Yep. 238 is 238. That means the atomic mass is 238. There's 238 neutrons and protons. So plus 238 equals 352. So that's how the book got that mass. So M equals that. So V RMS U238 F6 equals square root of 3 8.31 joules per Kelvin, 300 Kelvin over 350. Okay, so this means that 1 mole equals 352 kilograms. Am I thinking about that correctly? Grams. We have the 1 mole. This is the uh, molecular mass, 352. 1 mole of this substance weighs 352 grams, or 0.352 kilograms. We're going to put 0.352 kilograms in standard units. So that's going to equal, let's see, 331. So I get left off 2 zeros. So I have 145 meters per second. Right? We have K, it's canceling K. Joules is kilograms meters squared over second squared. So the kilograms cancels out. We have meters squared over second squared. The square root of that is meters over second. So that's that. And instead of the molecule containing uranium-235, the molecular weight is only it looks like, read the book again. And that's one thing about these problems is understanding exactly what they're asking. Instead, the molecule contains uranium-235. The molecule weight is only 349. Makes sense? There's three differences between 35 and 38. So M2 equals 349. That makes sense. So if I put that in for 349, it gives me 146.146 meters per second. So, and it actually was able to get the factor of the difference of the speed. So if I divide 352 by 349, that gives me 0.08. And if I divide 146, actually, let me use the actual numbers. 146 dot something divided by 145 dot something. It also equals about the same. V over V equals 1.004. So since the only thing that changes is the mass, the fraction of masses is about proportional to the fraction of the speed. I believe I got this correct when I did the homework. Next is 123. '23 says calculate the total thermal energy in a liter of helium at room temperature and atmospheric pressure. Then repeat the calculation for a liter of air. All right, so they're using the thermal equation, which I'm pretty sure I have on my formula sheet. That's this one here. Calculate the total thermal energy liter. Okay. Helium has 3 degrees of freedom, so I might have gotten that wrong. So let me look at this. So just He by itself. That's the degrees of freedom for the molecule. So we have that for just a single gas. A solid is 3 as well. So we have it equals this equals F1 over 2 in KT. PV equals N big RT equals little n equals NKT. I think I have that one equals NKT. PV equals nRT equals big N KT. Right. So this equals F1 half PV. And it says it's at room temperature and atmospheric pressure. So P equals 1 atom, V equals 1 liter. So we have 3/2. I have it on my formula sheet. Atmosphere is 10⁵ PA, is newtons per meter squared. Copy this. Equals 3/2 e⁵ newtons over meter squared. And 0.1 meters cubed. It's 1 liter. So we have newtons times meters, which is joules. So that'll give us the proper units. Let's see what we have. We have 150 joules, which is what the book says. So have to remember that shortcut. Remember that you can use the equation. This is the default thermal equation, but they give us pressure and volume. But remember that big N kT equals pressure times volume for an ideal gas. So thus you could insert PV for that and solve given what they gave us. All right, so good stuff. And the next problem is 125. List all the degrees of freedom, or as many as you can, for a molecule of water vapor, right? So let's put this here. So we have translational, like any other gas molecule, a water vapor molecule has 3 translational degrees of freedom for motion in the X, Y, and Z direction. But this will technically be relational. There's 3. Rotation, a water vapor molecule has no axis of symmetry, so it can rotate about all 3 perpendicular axes, giving 3 rotational degrees of freedom. That makes 6. Vibration, a water vapor molecule